Hey guys, this is just going to be a standard moment example. What I'm going to do is I'm going to provide you an example of a rigid body which is bent out of proportion, and there are going to be two external forces acting on that rigid body, and I'm going to ask you the question of what is the external moment as a result of those forces. Let me draw that for you. So you've got a rigid body. Let's say it looks something like this. It could be a bent screwdriver or something. Oops. It could be a bent screwdriver or something like that. And it has two forces acting on this particular object. One force could be this one just here. This could be, I don't know, 3 newtons just there acting in that particular direction, and the other one can be, I don't know, let's say right here acting at this point. Actually no, let's make it a little bit more interesting. Let's say it's acting right here on this point just here. Maybe, I don't know, let's say that's 6 newtons just here. Right? And maybe just to make it a little bit more interesting, let's add a third force acting just this way, and let's say it's 9 newtons just there. And we wanted to find out the net moment acting on this rigid body as a result. In order to do that, we need to know some dimensions of this rigid body, which I've drawn just here. Well, for starters, let me just describe this rigid body just here. Let's say that this dimension from here to here is going to be equal to, I don't know, 3 meters. And let's say that this dimension, let me find my mouse again, this dimension just here is going to be, I don't know, let's say 4 meters long, just there. And let's also say that this particular angle subtended between this part and the horizontal is going to be 30 degrees. Just going to draw that just there. 30 degrees. Alright, now our question is to find out what is the net moment acting on our particular rigid body diagram. So, if we were interested in doing a force balance, we could easily see that the forces acting to the right, 3 and 6, are equal to the forces acting to the left. So we know that the sum of forces is equal to 0 in this particular case. That's quite obvious. But are our moments equal? Let's find out. So by definition, the magnitude of a moment is going to be equal to your magnitude of your displacement vector times by, multiplied by, your magnitude of your force vector. Right? And the sum of moments is just going to be the sum of all these different magnitudes due to each of these forces. So let's consider, I don't know, let's call this one, let's call this 3 newtons, let's call that force 1 right there. And we'll call this 9 newton force, we'll call that force 2, and we'll call this 6 newton force, we'll call that force 3. So let's consider force 1 first. In this particular case, Actually, yeah, okay, let's do force 1 first. So in this particular case, the magnitude of r is not going to be equal to 4 meters. It's not going to be this distance from our axis of rotation, which I've chosen to be here, although I could have chosen any particular point. It's not going to be the distance from here to here. It's instead going to be from here to here. Let me explain why. So, let me just draw this distance just here. Bam. Bam. That is going to be the magnitude of R1. That is going to be this particular part just here. So if we're interested in M1, our magnitude of M1, it's going to be equal to R1 times by our magnitude of F1. Right? The reason why it's this distance and not this distance is because our distance from our axis to our force vector must be perpendicular. Notice how this is perpendicular just here? Whereas if I were to draw this one as R1 with a magnitude, that would not be perpendicular. That'll be at some angle. Specifically, it would be 30 degrees, which is not 90. It needs to be perpendicular. That's crucial to understand here. Basically, this term just here must be perpendicular to our force vector. I cannot overemphasize that. So If we want to calculate m1, our magnitude of m1, which is just our moment due to f1, then, or force just here, what we can do is we can simply find out what the magnitude of r1 is and multiply it by f1, which is our 3 Newton force. In order to find out r1, we simply use simple trig. Let me draw that just there. Actually, yeah, I'll just keep going in green because it's easier. We know that this distance here is 4 meters, right? We know that this angle here is 30 degrees, right? Just a Z triangle just here. And we also know that this is R1 just here. If we wanted to find R1, the magnitude of R1 I should say, that's simply just going to be 4 sine 30. And sine 30 is just equal to a half, so that's just going to be equal to 2 meters. So, if we were to now redraw this, we can go, okay, well that's just going to be equal to 2 meters times by 3 newtons, which is going to be 6 Newton meters. This is the moment this is the external moment acting on the rigid body as a result of our force 1 of 3 newtons. But we're not done yet. That's just one moment taken into consideration. We need to consider the moment due to F2, and we need to consider the moment due to F3. So, now let's use a different color to describe this. I'm going to use, I'll use blue. Actually, no, I'll use red. It'll be a little bit less convoluted that way. If we're interested in M1, which I'm going to define as the moment being induced by our second force, that's going to be R2, the magnitude of R2 times by the magnitude of F2. Right? It's a scalar if we're dealing with magnitudes. So, in this case, what would R2 be? Well, that seems a little bit confusing, doesn't it? Because it doesn't seem to have an R2. The distance between here and our force vector is 0. And that's exactly what it is. This distance between here and here is pretty much 0. Well, it's exactly 0. 0 times by our force, our magnitude of our force, which is 9 newtons. Consequently, the moment due to our second force acting on this object is 0 Newton meters. Make sure this satisfies your intuition as well. Imagine if you had an axis of rotation just here and you applied a force just there. It's not going to rotate at all. It's just going to be it's going to try to be shifted left a little bit, but it won't really go anywhere because there are other forces keeping it in place. So there's no moment being induced by this second force. And for our third moment due to our third force, I'm going to use blue just here. Moment 3 is going to be equal to the magnitude of R3, which is going to be our perpendicular distance from our force vector to our axis of rotation, multiplied by our magnitude of F3. Alright, so I haven't actually drawn this too well, but let's now say that this distance just here, let me try and find my mouse again. We need a little bit more information to solve this. So let's say that this distance from here to here is actually just 1 meter. So this distance from here to here is 3 meters, but this distance from here to here is 1 meter. So what do we use for R3 in this case? Well, using simple mathematics, we can tell that the distance from our axis of rotation to our force vector, if we were to continue this across, is going to be equal to 2 meters. Right? Notice that it's perpendicular as well. Right? As a result, we can rewrite this as our magnitude of our moment 3 is going to be equal to 2 meters multiplied by our force, which is going to be equal to 6 newtons. And that's going to be equal to 12 Newton meters. But that's not enough. Although we've calculated the magnitude of our moments, we also need a direction, because moment also specifies whether it's going clockwise or anti-clockwise. It's a rotation, right? So a magnitude is meaningless. Let's view M1 again to determine which direction it's spinning, and we can use just our basic intuition to try and solve this as well. So let's try and think about what this would be. If we apply a force just here with an axis of rotation just there, which way do you think force 1 will want to spin this particular object? It would be clockwise, won't it? Just imagine like putting your finger just there and pushing the top of this bit just there with another finger. Your object will try and spin clockwise. So I'll just put a CW there denoting clockwise. Now we've already discussed that the moment of our second force, the moment induced by our second force, is actually 0. So it's neither clockwise or anti-clockwise. So I'll just put a blank there, just right there. And how about this bit just here? If you put if this entire object is spinning around this point just here, right, and you apply a force of 6 newtons going positively to the right, which way do you think this object is going to be trying to spin as a result of just this force? Well, it'll be counterclockwise, won't it? Just imagine it. You put a finger here and you push it just there. It's going to try and spin this way. So this is going to be counterclockwise. So this may be a little bit confusing to you, because now we've got 3 completely separate pieces of information. We've got this object wants to be pushed counterclockwise, it wants to be pushed clockwise, and it doesn't want to be pushed at all in terms of moments. So which way does it actually rotate? In order to figure out, we need to take the sum of moments. The sum of our moments, right? It's going to be equal to, let's say, we could choose, depending on which way we want it, we could go clockwise subtracted from counterclockwise. Don't mind my handwriting, but hopefully this will make sense to you. So if we were to sum up our total moments, our clockwise, all of our moments going in the clockwise direction is just m1, which is going to be equal to 6 Newton meters. And then we subtract that from our counterclockwise direction, which is going to be equal to 12 Newton meters. And this will give our answer of negative 6 Newton meters clockwise. So what does that mean? It means this object is going to be rotating with a moment of negative 6 Newton meters clockwise. It's going to be rotating, the sum is going to be rotating at negative 6 Newton meters clockwise. In other words, you can say it's going to be rotating at 6 Newton meters counterclockwise. That is your answer. That is your answer. So make sure this actually make sure you kind of understand the intuition behind this. If you have a whole bunch of different forces acting on a rigid body, each of those forces will have their own separate moment induced on a rigid body as a result. You find each component of their moments, you sum them all up, and then when you sum them all up, you're left with one final answer, and this will be your net moment on your rigid body. In this particular case, it was 6 Newton meters counterclockwise.